Hi, my name's Ian Searle, and I'm going to be talking a little bit about Hall effect sensors today. We're going to go a little bit over what they are, how they work, how they're built and designed. Then we're going to go over a few uses, popular uses, as well as a few other uses that are less common. And then we're going to review kind of what we've learned. So first, we got to talk about the magnetic Hall effect. So due to the properties of electromagnetics, when an electric field is passed over a current, it creates a small voltage difference in the material that it's going through. So this was discovered by Edwin Hall back in 1879. So we've known about this principle of physics for quite a while. It is formed by changes in electrical flow through a conductor. It requires a magnetic field, a current, and a conductor. The Hall effect, the Hall voltage is the slight change in that electrical potential through it. So we can see here on this diagram that here in figure A, we have different electrons moving through a material, through the battery, which is the voltage source. The magnetic field is 4 between the two magnets. And you can see this red and blue. That is the slight charge difference in the conductor itself. So the electrons are going to take the path of least resistance. As they go through, they're going to slightly move up towards a voltage or down towards the voltage, depending on how we have it set up. You can see that is a various setup through these different images. Each one causes the Hall effect to work a little differently. So the way it works in the semiconductor devices is moving back. We can detect this slight change in voltage as a material. So we have a Hall effect sensor. As a magnet comes close to it, it's going to change that voltage. It's going to change how different those two levels are. From there, we can measure that. So here we have just a basic schematic I got off of a TI Hall effect sensor. So we use it using modern semiconductor processes. The Hall effect, the Hall element, which is this represented by this cross element down here in the middle, is detecting the magnetic field. So we supply a voltage, and then they have some temperature compensation because as the voltage, the material changes at different temperatures. And then as it's going, it goes through, it goes into an op amp to amplify that voltage. And then it goes through an output driver to up the current, which we then are using. So the amplifier and driver, like I said, you take it from a non-usable level to a usable level. And then some digital sensors even have a DAC built in to output the a binary or digital representation of the voltage, while what we're looking at is an analog representation. So there's a few different applications for these things. The two main ones are speed and position measurement. So you can know how far something is moving based off how many sensors you have, and you can, if you line them up linearly as you move across, you can detect how fast it's moving by each one. You can also read how quickly its magnetic field strength changes. You can also look at when things move, if they're separated. So a common one for this is alarm systems, items moving out of bounds of certain regions. A lot of conveyor belts use these. So specific uses is security systems, like we were talking about alarm systems. Well, what happens, you'll have these in places that can open, such as doors, vents, windows. Some people can put them on drawers, safety things such as saves, just so you know when it opens up and it can trigger an alarm. An alignment system, so it can make sure things are aligned by having the right magnetic field strength at any given point. Motor speed control, this is actually a very popular use that I forgot to mention earlier, is in order to get rid of brushed DC motors, we move to using Hall effect sensors. Due to how motors work, they create a magnetic field. This magnetic field, as it rotates, changes the voltage on each Hall effect sensor, allowing it to flow more evenly through the motor, which is how we can build brushless DC motors. Switches, some people use them as switches. It would be similar to how they use it in security systems, whether it's closed or not. Those are often called reed switches, but you can use a Hall effect sensor. They're often used in reed switches, although you can use just a Hall effect sensor. Machining tools, they are once again used for high precision applications there to know where something is, how fast it's moving, or even how fast it's rotating. Current sensors. So we know that a steady current generates a magnetic field. If you put these sensors in, you can detect how what the current is through that wire based off the magnetic field strength. Braking system. This is another very popular one. When you push on the brake, it will move the panels, and you can see the magnets will tell you when you're pushing, how hard you're pushing. Proximity sensors, you can detect how close something is based off a changing magnetic field or if it generates its own magnetic field. These are all over MRI machines. I couldn't find a specific application. They're used in thermostats, specifically when you're using a rotary knob. What you'll do is you'll move a magnet relative to one. Joysticks, a lot of modern joysticks use Hall effect sensors. Electric bikes are often used there too to know how fast your wheel's moving, as well as when you're doing the regenerative braking and inside the motor itself. And then you can also use them for encoders based off if you have, this is the example right here. You can count how many times the Hall effect sensor triggers, and that can tell you how many rotations you've done. And so, in conclusion, Hall effect sensors are very common and are used in a variety of applications. They're vital to many modern day products, such as the electric car, fans, and a lot of household and security system products. And they are a vital showcase of electromagnetic principles in action. Because we're seeing how that voltage difference is, we're able to read it, we're able to understand why it's happening and predict it so we can design sensors that can read certain magnetic field strengths as well as magnetic flux strengths. Thank you.